Hello, this is video 46. We're doing the last topic related to this unit where we're talking about energy and work. So here we're talking about power. So I'm sure you know that if you are walking up the stairs with a heavy box or running up the stairs with a heavy box, there's a big difference. You feel a lot more tired if you run up the stairs. So that's because you're exerting more power. Power is the rate at which you're doing work, or also the rate at which energy is transferred, because work is a transfer of energy. So the faster you do work, the more power you are exerting. So power, capital letter P, is work over time. Work is force times distance, then divided by time. And then we can say, okay, well, a distance divided by time is going to be a speed here. So we have force times speed as well for power. So we can use whichever definition is more convenient for us. But the conceptual thing is that now we care about how long it takes to do this amount of work that you're doing. Remember, with the transfer of energy, we're talking about, let's say that you are lifting that box up the stairs, then you are giving that box gravitational potential energy. So that's why we're saying it's a transfer of energy as well. So the unit for power is the watt, and power is a scalar, so we don't have to worry about any vectors here. Now, you probably have heard of horsepower as a unit for maybe how powerful the engines are in your car. So horsepower is just not an SI unit, but this is the conversion factor that it's 1 horsepower is 746 watts. And lastly, if you have heard of kilowatt hours, maybe you pay your electric bill and you've seen it on those. Well, kilowatt hours, although it has that watt in there, it is not a unit of power. It's actually a unit of energy. As you can see, kilo is just 1,000, right? So 1,000 watts times multiplied by hours. You have a power multiplied by time. If you go back to this definition here, if you multiply the time over, you get work. So work has units of energy, so this is just telling you that kilowatt hours is a unit of energy. Those electric companies, they bill you on how much energy they use. They don't care if you use it all in one day or over a span of 30 days, how quickly you're using it. So we're going to do a conceptual question and then an example for power. The conceptual question, your turn here. It says that engine A has a greater power rating than engine B. Which of the following statements correctly describes the abilities of these engines to do work? So, engine A is more powerful. So, with the definition of power is work over time. In order to have more power, you can either do more work, and then that means you're more powerful, or you can do the work in less time. The time is in the denominator, time is smaller, the work is bigger. So they're definitely not doing the same work in the same time. In the same time, engine B can do more work? No, because engine A is more powerful. So engine A and B can do the same amount of work, but A can do it more quickly. So it's the second case right here, where you do the same work in less time, makes you more powerful. Let's do one example. So you'll find that this topic of power is going to be one of the easier topics. It's just going to be kind of a plug and chug thing. It's not a very detailed and long problem. So here we have a crane can lift a 200 kilogram mass through a vertical height of 5 meters in 4 seconds. So we have the mass of 200 kilograms. We have the height or the distance here, 5 meters, and we have a time of 4 seconds. What's the power output? So the crane has to do work to lift the mass, and it's doing work in a certain amount of time. So we can find out the power. So I'm going to use work over time, which is force times distance over time. You can use delta x or d for distance, doesn't matter in this case. So we have to figure out, well, how much force does the crane have to apply? Well, to lift something up, you can lift it up at a constant velocity, and then your force just has to balance the weight. the picture shows a greater force here, but they just have to be equal. When force is balanced, you're in equilibrium, and you can move at constant velocity. So we just need that force to be equal to the weight. So we'll just plug that in, mg times distance over time. Then we can plug in the numbers. I'll let you plug them in. 200 times 9.8 times 5 divided by 4, and we'll get 2450 watts. So that's how powerful the motor is. So since a watt, let's see if we go back, a watt was about 746 watts was 1 horsepower. So that means I haven't done the math, but this is between 3 and 4 horsepower for this motor. So that's it for this very short little section on power. Power is just how fast you're doing work.